name is Michelle Vamos, and today I'm going to walk you through my Is It Science or Magic program. This program is going to be a whole bunch of different experiments with things that you, with supplies that you should already have in your house. So I'm going to walk you through a whole bunch of experiments, explain why it's happening, and then you can tell me if you think it's science or if you think it's magic. The first experiment we're going to do today involves a ziplock plastic bag, some balloons, some water, and some pencils. So for all these experiments, please make sure that you have adult supervision, that you have an adult with you when you're doing these, because some things can get a little messy and some things, we just want to make sure that you're safe. So, like I said, we have a bag, pencils, water, and then the balloons. So if I was to fill this balloon with air and then take a pencil to it, what would happen, right? It would pop, make a loud sound. I'm not going to do that. But do you think the same thing will happen if I fill a bag with water and then put the pencils through it? So let's see. So you're going to take your Ziploc bag. You can use a gallon. You can use a little smaller, just you don't want to use it too small. Then you do this over a sink, or I'm just doing it over a little tub right now. So I'm going to fill my bag with water, get some of the air out, and close it. You want to make sure it's closed. Like I said, it's okay to have some air in it. I am actually, just so you can see this better, I'm going to put some food coloring in it. Again, you do not have to put food coloring. Maybe don't, just in case it does get messy, but I just want you to be able to see better since the water is clear. So, have our bags, mix that up a little bit. Close it again, make sure it's nice and closed. Now, like I said, right, if we had a balloon and we filled it with air or water and we put a pencil through it, it would pop, right, and all the water would fall out. So we're going to see what happens with the plastic bag. Right? I would think that just like a balloon it would pop, so let's see. So some of my pencils are super sharpened, some of them not so much, so let's see. Again, put it over the container and did it leak? Let's try it again. And then one last time for good measure. Did it leak? So why this happened is plastic, which the bag is made out of, is a polymer. And what a polymer is it's a chain of molecules which are flexible and tough. So what happens is when you put the pencil through, if you can see, the bag actually surrounds the pencil and makes a seal so that no water comes out. So pretty cool, right? Now, question is, what do you think will happen when I remove the pencil? Do you think the water will fall out? Do you think that it will close up again? If you want, you can try with different bags to see if they work. Again, make sure that it's somewhere that if you make a mess with the water, it doesn't go all over the place. So that was our first experiment. So this was an experiment with polymers. And I will tell you, when you take the pencils out, the water will gush all over the place. So I am going to put this in my sink. Okay, the next experiment we're going to do, you're going to need, you can either use a glass cup. I'm going to use a glass jar just because it's a little larger. Then usually in my programs, I have everyone write on an index card. I'm going to write on a piece of paper just so it's larger that you can see. But again, usually I have a jar and I give everyone an index card and I tell them to fold it like this. I always say in my programs, I don't know if you guys learned, but right, if you fold it this way, it's hot dog, this way is a hamburger, so I say fold it like the hamburger. And I'm going to do that with my big piece of paper. And then I want you to draw something that is asymmetrical. So do you know what asymmetrical means? Right? It means it's not even on both sides. So let's say I was to draw a circle. If I cut the circle down the middle, both sides are the same, so that is symmetrical. Same as the smiley face, right? If I was to fold it in half, the parts would go on top of each other. So you want to draw something that is asymmetrical, meaning it is not the same. So that can either be be a whole bunch of things, but for this, I'm going to draw 2 arrows. You could also draw a smiley face, but if you do a smiley face, you want to make it so that it's a little different, right? So that both sides are not the same. So right here, I have arrows going to, this is my left, and then I have a smiley face with the tongue to my right. So what you're going to do is you have your jar, and I'm going to put my picture, which again, you can do it on an index card. Put this, hold it up a little bit. Okay. Now if you look, I'm going to come around this way, right? All of the images are pointing to the right. I know I said left before, but now this is, should be your right. So images are not moving, right? They're staying the same. Now I'm going to take some water, and I want you to look through and I want you to tell me what happens. You want the jar to be about 4 to 5 inches from your image. So actually, let me come around again. So everything is pointing this way. Put the water through. And I don't know if you can see, I will do a close-up if you can't see that well now. Now the arrows are pointing this way. So same with our smiley face. His tongue is to the left. When we put him here, his tongue is now out to the right. If the image is not flipping, it means it's too close or too far away. So you just kind of want to move it a little to help you. So what this is doing, any idea what kind of science this is? This is called refraction. So what refraction is it is the bending of light waves. So what happens is we have the light and it's going through the air, then through the glass, then through the water in the glass, then through the glass, then through the jar, and it's flipping the image. So pretty cool, right? You can flip an image just by using water. Okay, so we have the image. The arrows are to the right. When we put it through the water, it refracts, and now the arrows are pointing to the left. And same with the smiley face. His tongue is out to the left. And when we put it under the water, as you can see, his tongue is now, it's a little difficult to see, but his tongue is out to the right. Okay, so the next one we're going to do is another one with water. Again, these are things you should all have at your house. So I'm going to take a glass cup. I think smaller is easier, but you can use whatever you like. Water. And then I cut up a cardboard box, which is small pieces. Doesn't have to be too big, too small. You just want to make sure that it's big enough to cover the top of your cup. So my question is, if I took this cup, right, it's empty, it's a regular cup, it's actually the ones that we drink out of in my house, and I put this paper here and turned it upside down and moved my hand, what's going to happen to the paper? Any idea? It's just going to fall, right? How about if I do that with an index card, right, a little thicker paper? Doesn't really actually fit over the whole top, but falls off. How if I do that with cardboard? Think it will make a difference? It falls. But what happens, again, do this over a sink or use something to catch the water. What happens if I put water into my cup? And let's do the cardboard first. Put the cardboard on top of the cup and make sure it's all covered and flip it upside down. What do you think is going to happen? Think it's going to stay? Think it's going to fall? Ready? No hands. Pretty cool, right? Will fall a little bit, but overall, no water really fell. Now let's try. I'm going to skip the index card because mine are not big enough for the top, but let's try with paper. Maybe I'll fold the paper. So cardboard works, right? What is thicker? Cardboard or paper? Definitely cardboard. Even if we fold this a few times, it's still not as thick and strong. So let's see, we have this. I am going to take a paper towel, just wipe the rim off just to make sure there's no water. And let's try it with the paper. Paper on top. When you do this with cardboard, whatever you're trying, you want to push down on it. Turn upside down. And let's see. Oh, not so much. So why did the cardboard stick to the cup and hold the water in? Any idea? So why it did it is because of suction, right? So you might see, actually in my sink, I have suction cups to hold the brushes to brush our plates off. In the shower, I have suction cups to hold our loofahs in our shower. What suction is it's air pressure, right? That is basically when we're doing this, the air pressure under the card is greater than the weight of the water in the glass. So, right, we fill it up with water. We have water here, we have air, and then we have the cardboard, right? And now we're switching so that the water is here, the air is here, and the pressure is so great that it holds it on just like a suction cup would. Pretty cool, right? Again, be careful because we are using water, don't want to make a mess, kind of like I did. And also, we were using glass, so we don't want that to break. I'm going to show you one more time, again, just to make it visually a little better. Again, I do not recommend doing this at home with the food coloring, but just so you can see. Get the granite a little clean. Put these here. I'm just going to put a little food coloring just so you can see a little better. But again, food coloring does stain, so there's only one experiment that you really need the food coloring for, and I'll let you know when. But besides from that, I just wouldn't use it just because who wants to clean up a whole bunch of food coloring, right? So I'll move this around. I will take another piece of cardboard and show you again, right? So we have the water that is green. We have air on top. And then there we go. Pretty cool, right? Okay, the next experiment we're going to do involves a jar, or you can use a cup. I'm using a jar just so it's bigger so you can see. Then you want an index card and a coin. So you're going to have the jar, index card, and the coin on top. What do you think is going to happen if I slowly move the card off of the jar? Do you think that the quarter that I'm using will stay on the card? Think it will fall to the side? Think it will fall straight down? Think it will fall up? What do you think will happen? Let's see. So I'm slowly going to move the card. As you can see, the coin stayed on the card. What happens if I move the coin fast? I mean, not the coin, the paper fast. Any idea? Do you think it will stay? Do you think it will fall? Let's see. Right. It fell right into the jar. So what happens if, again, my jar is just a little wet. If I do it a little slower, still filling. So any idea why this happened? So we have the coin, card, and the jar. This has to do with Newton's first law of motion, which has to do with inertia. Inertia is an object resisting change from the state of motion. So basically right now we have a jar, which is not moving, paper, which is not moving, and a coin, which is not moving. When I move the card fast, the coin falls down because of the friction between the card and the coin, which there is not much. So Newton's first law of motion, which has to do with inertia, is an object at motion tends to stay in motion, and an object at rest tends to stay at rest unless an outside force tries to change that. So what happens is, right, the coin is not moving. Then we're moving this, but the friction just has it fall right down. Let's say if we tried with different objects. Let's say if we do a Q-tip, how that would work. Did it fall in? Not so much. Nope. Let's try one more time. For any experiment, if you only try something once, it's not good enough. You have to try it multiple times. right? Because sometimes an experiment works perfectly, sometimes you do it again and it doesn't, so you have to do a whole bunch of different trials to see. 3 times didn't fall in. How about a balloon? So I want you to try with different objects. You just want to make sure that nothing is fragile, nothing can break if it falls. And also I want you to try with different kinds of paper, cardboard, to see if that matters. Oh, that one fell in. Right, so it really matters the friction. Oh, that one didn't. Let's see one more time. Nope. So it really matters the amount of friction, right? And this has to do with oh my gosh, I cannot say his name today. Newton's first law of motion, that has to do with inertia. For our next experiment, which is one of my favorites because it involves candy, we are going to be using a plate. You can either use one of your kitchen plates or you can use a paper plate, some candy, and some water. So I'm just going to grab some more water because my green water will not do. So when you're doing this, if you don't have Skittles, you can try another type of candy. You want one that has different colors. And then we're also going to try with different types of water. So what you're going to do is you're going to open up your candy. Come on, candy. And you are going to arrange the candy on the outside of the plate. You can do it by color, so if you want, you can put green, 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 then yellow, 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 orange, 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 all the way around, or you can just do it randomly. I'm just going to put them around randomly. Also, if you don't have enough Skittles to do the whole entire perimeter of the plate, you can make a smaller circle inside. So I'm going to put these down. Bear with me as I arrange them. And you want them all to be pretty close, but only one layer of them. So you're going to put the Skittles all the way around. Again, if you don't have Skittles, you can try with a different type of candy. So you can try with M&Ms, or you can even try with Nerds. And then we're going to start with some warm water. You're going to see how the warm water works. And then once you do this with warm water, then I want you to try with cold water and see if there's any difference. Okay. So we're going to arrange that. So after you have your Skittles in a circle, as much as you can, and again, I'll show you a close up in a little bit, you're going to pour the water in the middle, and you're going to cover the whole plate. So now I'm going to show you a close-up of the Skittle experiment. So we have the Skittles. I put them all around the perimeter of my plate. Then you're going to put the water. We're going to see what happens. So right now I'm using some warm water. But again, I want you to try this experiment with different types of water. So cool water, warm water, and let's see what happens. For this, you have to be a little patient. But as you can see, if I zoom in slowly, the colors are starting to go towards the center. I'll check back in a few seconds to show you. Okay, now if you look, all of the colors from the Skittles has dissolved into the water and pooled in the middle. So what this experiment has to do with is diffusion, which is the net movement of anything that has a higher concentration to lower concentration, and gravity, which is a force that attracts an object towards the center of the earth, right? So what happens is the gravity pushes all the colors in the middle. The food molecules are bouncing at random through the water, and then the sugar is more dense than the water, so the gravity pulls it towards the center. And after a while, it diffuses more and more. That's why we saw a little bit of diffusion, and the longer we went, the more we saw. Pretty cool, right? Again, you could try this. I just put random colors all around. You can put like colors together. Pretty cool. And also you can try it with the different temperatures of water. This next experiment has to do with a piece of paper. I bet you that I can walk through this piece of paper without adding anything to it or using tape or anything. All I'm going to be using is markers to help me a little bit and then a pair of scissors. Any idea? So I want you to take your piece of paper and I want you to try to cut it different ways. Fold it different ways using your scissor, and tell me if you are able to walk through your piece of paper. So I'm going to show you how to do this. So you're going to take a piece of paper and you're going to fold it like I showed you before, like a hamburger, not a hot dog. Then you are going to draw lines. You want to start where the paper is folded, and you want to make a line from the bottom almost all the way to the top at the beginning of this end and at this end, okay? So it's a line almost all the way to the top, stop, then a line from the top almost all the way to the bottom, stop. And you're going to do that all the way down, okay? Then you're going to take your scissors and you're going to cut on those lines. You have to make sure that you do not cut all the way to the end. So it's kind of going to look like a zigzag. The closer you have these lines together, the bigger your paper will be. Also, I just want to make sure I mention that my whole body is going to go through this piece of paper. A lot of times in my programs, I say, yeah, say to your parents, I bet you I can walk through this piece of paper, and if I can, then I don't have to do the dishes, or I don't have to make my bed. And let's see if you can do it. So again, you're just going to cut, cut, cut. If by mistake you call the way down, that's okay. Just grab another piece of paper and start over. And again, the two ends have to be where this end is open, okay? You're going to cut down. Then, well, you can see this, okay? You are going to leave these two ends intact. You're going to take all of these parts and you're going to cut them. So again, this part's staying put, cut here, cut here, you're starting to see it. Whoever knew a piece of paper could get so big. And then a few more, and don't forget, we're going to leave this one together. Are you ready? And ta-da! I made a piece of paper big enough that probably my whole family could walk through. Remember, are these things science or magic? You tell me.
So for the paper walkthrough, the paper still has the same properties as the paper. The only change in the paper is a physical change. A physical change affects the form, not the chemical composition of the paper. So by cutting the paper, we just make it larger than it originally was.
Okay, the next experiment we're going to do is a body trick just using your body. So all you need is your hands and your feet. So what you're going to do is you're going to take your right hand and you're going to draw a 6 in the air. Okay? Then you're going to take your right foot and you're going to rotate it clockwise. So it's going to go around like this. So you're going to rotate your foot. And then you're going to draw a 6. And guess what happens? Your foot went from going clockwise to counterclockwise. Any idea why this happens? So basically, the left side of your brain controls the right side of your body, and the left side of the brain works with rhythm and timing. So what happens is your body is trying to do two different things, and it can't do them at the same time, so then it just makes them all try one motion. Now I want you to try it maybe with your right hand, your left foot, right hand, left foot, and tell me what happens. For the next one, it's another fun one. We are going to be using a plate, some whole milk, some food coloring, so you do need food coloring for this one, some dish soap, which I'm using Dawn. I just had a little extra in here, so we'll use this container, and some Q-tips. So you want to make sure that you have whole milk. If you don't have whole milk, you can try with other milks and see what happens. But right now we're using whole milk. which if you don't know the difference from skim milk or 2% milk, whole milk has a lot of fat in it. So if you're used to drinking skim milk and you drink whole milk, it's going to taste like a milkshake. If you're used to drinking whole milk and you drink skim milk, it's going to taste really watered down. So we are going to pour some milk on the plate. Again, you can use a plate that you use for dinner, or you can use a paper plate. And you just want enough that you cannot see any of the bottom of the plate. And then you're going to pick a few colors of food coloring. I'm going to pick blue, yellow, no, it doesn't look yellow there, and green. And you're going to put a few drops onto your plate. So maybe put 3 of each. So I did 3 drops of blue. Again, don't help with this. Food coloring will stain your hands, it will stain the floor, so you really want to be careful. Some yellow, and then some green. Now there's different ways you can do this. You can put a little more food coloring, or you can just do a little bit. If you do a lot of food coloring, you're going to take your Q-tip. Either way, you're going to take your Q-tip and you're going to dip it into the dish soap. If you have a big portion of color, you can dip it in the soap and dip it into the color. Or what I like to do is dip in the soap and dip it into the middle where it's just milk. So we're going to take your Q-tip, put some soap on it, and watch what happens. Again, I will give you a close-up so you can really see. I know it's hard to see here, but what happens is this really shows how soap works. So we have our milk. Milk is made up of fat and protein. So we have our milk, then we have our soap. What do we usually use dish soap for? We use it to clean our dishes, maybe sometimes our hands, right? If our hands have grease or fat or different substances on our hands. If we just wash our hands in water, does it do much? Maybe it gets a little something off, but if our hands are really, really messy and we use soap, right? Usually we use hand soap. When this is dish soap, this is more concentrated. What it's doing is showing the interaction with the milk and the soap. Okay, so what happens is the soap latches onto the milk. The food coloring we just have here so you can see what happens, because if we didn't have the food coloring, you wouldn't be able to see the reaction. So the soap latches onto the milk, and what happens is it bonds to the fats, and that's how we see the reaction. Also, this is also showing surface tension. So we have our milk, which if you have water or milk, you kind of see it has, right, a surface, doesn't really move. When we put the soap, it disrupts the surface tension. So I want you to try this with different milks or different liquids and see what happens. What else would we do this with water? Would it work with water? Does water have fat in it? Does water have proteins? You could try it with orange juice. I want you to try it with different things and tell me what happens. Again, I will show you a close-up of this so you can see exactly what happens. Okay, so now we give you a close-up of the milk experiment. You want to take the milk, pour it so it covers the plate. Then I'm going to take my food coloring, do a few drops of each. Then I'm going to take my soap. I'm going to put it in the middle. Isn't that cool? You can even move it over here. Do it again. The more you do it, the less it will move. Pretty cool, right? Our last experiment has to do with a water bottle, balloons, baking soda, and vinegar. You may also want a funnel and a little cup for this experiment, but we are going to fill a balloon without using our mouth, by using all of these things. So I'm going to take a balloon, and I want you to take 1/4 cup of vinegar. So this is a 1/2 cup, so I'm going to use half of that, which is 1/4. And you're going to pour the vinegar. I'm using white vinegar. You are going to pour it into your water bottle. So for this, again, I am going to use food coloring just so you can see it better. Again, food coloring is not needed, and I would advise against it, just so that if it does spill, it doesn't make a mess. And I'm going to put a few drops of food coloring. Then, into our balloon, you're going to take the funnel, put it on the neck of the balloon, and then you're going to take some baking soda. You don't need too much, you don't need too little. You just kind of want to fill the bottom of the balloon. I'm going to even take a Q-tip just to help it kind of get down into the bottom. Just put a little more. Just pushing it down so it's in the balloon. Ooh, that seems like a good amount. Put it out here. Some might come out a little bit, so you just want to do it over a bowl. Okay, perfect. Now I'm going to take the balloon. I'm going to put it over the neck of the water bottle. Again, just make sure, since we're using balloons, these are made out of latex, just make sure you're not allergic to latex. Now I am going to take the balloon, put it upside down, and the baking soda is going to fall into the vinegar. Any idea what is going to happen? So we have vinegar and baking soda. When we mix these, it has a reaction, a chemical reaction. Right, so we have two different substances that when are mixed, make a different substance. So I'll explain what that is, but let's first see what happens. Pretty cool, right? Look at that go. So what happens is when the baking soda and the vinegar mix, it makes a new substance called carbon dioxide. Have you guys ever heard about carbon dioxide before? Right? As humans, we breathe in oxygen and we let out, you got it, carbon dioxide. So this is basically like we are blowing up the balloon. So next time you have a party and you need to blow up balloons, why use your breath? You can just make carbon dioxide on your own, right? Awesome. Thank you guys so much for joining me. It's always a pleasure doing programs with you guys, and I hope you enjoy these experiments. If you have any questions or comments, feel free to email us or comment below, and let us know if you tried out some different items, right, in your experiments. Maybe you did M&Ms instead of Skittles, or maybe you did more vinegar or less baking soda. Let us know. Again, thank you so much. It's always a pleasure, and I'll see you soon.